In this video, we'll go over the homework that follows the second part of the lecture on convergence of a sequence, and in this one we focus on figuring out the convergence of a sequence defined recursively. And the main idea here is that we'll be using what I called the 5-word theorem that states that a bounded monotone sequence converges, and this will be the only tool that we have for identifying the convergence of a sequence defined recursively. So we need to know how to figure out whether a sequence is monotone and bounded. And as always, I hope you watched this lecture, so let's go ahead and get started with the homework. And this is the first homework, and the first question is on identifying whether a given sequence is bounded. So to be bounded means to be bounded above and below, and the easiest way to identify whether a sequence is bounded is to maybe graph it, but every graph should be supported with some sort of analysis. So let's go ahead and take a look at what this looks like, but at the same time, what do we know right away about this sequence is that it's definitely positive, so it's bounded below, and whether it's bounded above or not, that's the question. But it seems like as n increases, things just get smaller and smaller and smaller, so it is fair to say that it's bounded above by 1. So intuitively I know that, again, it's going to be bounded, but it doesn't hurt to graph it and see what's going on. So we have 2 over 6n plus 3 and 1, 2, 3, 4, and you see how, again, how do we know it's bounded? Because we can graph this line y equals 0, y equals 1, and all the values of this sequence are between those. Is it true that it's bounded by other values? Yes. So if it's bounded, it's bounded. It doesn't matter how tight is the bound. Bounded just means such bounds do exist. And in this case, we conclude that it is bounded. Although this sequence is defined by the general formula, the 5-word theorem, also known as the monotone convergence theorem, can be or may be used for sequences defined by the general formula, and although the primary use of this theorem will be for sequences defined recursively, but anyway, here, in order for us to use the theorem, we have to develop the fact that this sequence is monotone and bounded, while I have no doubt that this sequence is bounded. Why? Because sine ranges from -1 to 1. That means 8 sine ranges from -8 to 8. That means 5 minus 8 sine will be ranging between -3 and 13. However, so this implies that it's bounded. However, to establish the monotonicity, the sequence have to possess either decreasing behavior or increasing behavior. And in this case, because sine bounces up and down, this sequence simply will not have that monotonic behavior, so we cannot use that theorem in this particular case. Now let me graph this just to show you what I mean. You see, this is not something that we would call a monotone sequence. So the answer here is convergence cannot be determined using this particular theorem. Convergence can be established using other theorems, or in this case, this sequence may not even converge at all. But it's not because of the theorem. Theorem simply cannot be used. Here's another example of trying to understand what a monotonic sequence is. I call it monotone, which is just as good. And in this case, to establish the monotonicity, we have to check how the nth term relates to the n plus 1th term, its successor. So I'm not sure even if I'm gonna go for increasing or decreasing, so I'm just gonna compare n plus 1, nth term with n plus 1th term. So I'm just gonna replace n with n plus 1 and see what happens. So again, we don't know what's going on here. So everything is positive, so we can multiply by the common denominator. So let's multiply by 4n times n plus 1. So here we have n plus 2 times n plus 1. Inequality did not change, it's still the same. Here we have n plus 3 times n. And now we have n squared plus 3n plus 2. And here we have n squared plus 3n. And clearly 2 is always greater than 0. That means this is always greater. That means this is always greater. That means this is always greater. That means an is always greater. And if your successor is always less than its predecessor, then the sequence is decreasing, and therefore it's monotone. You can also see that from the graph. So you see how it's constantly decreasing. We have seen this one before. And although an is bounded, so it goes between 6 to 12, I don't think we can establish the monotonicity here because sign is bouncing up and down, so it's not monotone, therefore convergence cannot be determined. And it looks like we finished this homework, in which we pretty much covered only the definitions of monotone and bounded sequence. We never got to use the theorem, sadly.